All right, it's 1:03. I think we'll get started. Welcome everybody to this ATA Engineering webinar, where we're going to be focusing on STAR-CCM Plus and HEEDS, and really looking at how to deploy that in the cloud, especially with Rescale. So I'm Adam Green. I'm a business development manager for ATA Engineering, and we also have Eric Timmer from Rescale, who's going to be talking for a little bit, and then Chris Ostoich from ATA Engineering, who's done the most of the work on this project to actually show us a demonstration case of this exact process. So I'll kick off now with just an introduction to ATA. And so here's our agenda, and really at the moment everyone is muted, basically to keep the ambient noise down from all the phones that we have online. At the end of the third presentation, we'll release the mute, and everyone can talk and ask questions as needed. So I hope that works for everybody. And so we're going to break into three parts. As I said, mine will be the first presentation, and then Rescale, Eric will give us some insight into what Rescale is and how it works. And then Chris will show us the STAR-CCM Plus HEEDS process that we've been working on for the last month. And so who are ATA? We're an employee-owned company, and basically a very highly skilled team of engineers, with over 28 PhDs, and really kind of very elite in terms of engineering, consulting, and services. We tackle the hardest jobs around, and really enjoy doing that as an employee-owned company. And the industries that we work in aerospace, we work in robotics and controls and defense primarily. We've also more recently done some themed entertainment work for Disney and Universal and some of those other groups where they need engineering consulting for the extreme rides that are kind of coming into the marketplace for themed entertainment. But really the aerospace and the robotics and control side is really our key markets and where we thrive. And so a lot of people have never heard of ATA, and that always kind of surprises me. But when you look at the history of ATA, the origins were back in 1975 when SDRC was around, and they actually had an engineering consulting group based in San Diego. SDRC were predominantly in Cincinnati, Ohio, but at the end of the nearly 2000, they were purchased by various groups, EDF, and in the end Siemens. But during all of that shuffling of companies, if you want to call it that, ATA basically came into existence as a management buyout from SDRC. So a lot of the team at ATA have been around since those days, very early days of ideas and unographics. And so the actual length of engineering excellence is just amazing. And because of that, we have really close ties to NX and to FEMAP, and still maintain, a very high level of relationship with Siemens to support and do training for those kind of things. And you can see on the timeline here, we've grown consistently over the years, and I'm not going to read it out, but we have offices in Denver and in Virginia, and most recently in Berkeley, California. So we're growing not super quick, but basically very robustly. And it's interesting, we're an employee-owned company, and really what that means is that all of us have a vested interest in making our clients successful and happy. So it really is a pleasure to work at ATA, and really that translates into very satisfied customers, and it really works very well. And the other thing about the work we do is we cover the whole gambit from design through analysis, including simulation, right the way through to test. And historically, test has been the mainstay of our business over the years. We've done a lot of tests for basically many large projects, ground vibration testing for space shuttles and things like that. Really big projects that require a lot of expertise in a very niche area. And so that's the biggest part of our business, but the software and the analysis side, as well as the simulation consulting, grows every year, and really is becoming a big part of our business. Our offices are mostly in aerospace kind of centers in the US, obviously the West Coast to cover some NASA and JPL sites, and then Huntsville is another aerospace center. So you can see where we're located nationally. And so we're not going to talk too much about the test and the other pieces today, but really the key thing is that ATA are one of the premier value-added resellers for Siemens, and we sell and support most of the products that Siemens produce, which is a lot, as most of you know. And so most of the Simcenter products, STAR-CCM Plus, HEEDS and AIM-Sim, FEMAP, all of those we sell and support. And so it's a big part of our business and is growing continuously. And so we're also very close to Nastran and also to FEMAP too. We have kind of a special relationship with Siemens on those products because of our history and our lineage to those tools. And as part of that, we support a lot of those tools, and with Siemens obviously growing and buying companies, that support piece is sometimes in transition. But you know, we started with FEMAP and Nastran, and when we're growing into the Simcenter products, and really, you know, over the next year, that's going to become a stronger and stronger piece of our business. The support, the training, all of the other pieces of the Siemens Simcenter products. And so really today, I'm going to be talking about kind of two key pieces of software. One is STAR-CCM Plus, which, as many of you know, I think there's some Siemens folks on the line too. You know, it's the premier CFD tool, multiphysics, and really this slide, you know, it shows just the diversity of the tool in the things that it can tackle. The goal today isn't to highlight how great STAR-CCM Plus is, even though it is great, but really just to show an interesting workflow that we'll look at in a minute. But STAR-CCM Plus is one of the key pieces of our business and of the presentation today. And so when you look at how people can use simulation tools, and this is STAR-CCM Plus highlighted here, but it really could be, you know, any simulation tool. The way most companies use it is that they're looking at either problems in design that's in the field and that needs to be improved, or they're looking at basic design. And really that third box there, the design piece, is the first box where it becomes predictive. And over the last 20 or 30 years, where CFD has really, you know, started to come on as a mainstream tool, kind of people have moved to the right a little bit slowly. You know, and design is really where most people kind of sit nowadays to actually use or use CFD generally, but especially STAR-CCM Plus. But the more value can be had if you move to the right here. If you can automate that process and actually tackle a lot more designs. And in the end, if you can do that, then if you can explore, then you can just get basically more value out of the same tools that you have. And so really Siemens and ATA's, you know, message is that moving to the right to do more automated design and more exploration of design spaces is really the future. And with computers getting, you know, cheaper and cheaper by the year, and power going up and up, this is becoming more realistic. So we're talking today about two pieces of software, really. One is the HEEDS tool, and this is just really one slide to highlight what HEEDS is. And HEEDS is predominantly a design space exploration tool, but really that breaks down into four kind of separate areas. And this is an example of an FEA model of an automotive front bumper, which there's an Aston Martin here that is being used. So that's obviously a high-end brand, but nonetheless, when you look at the four bullets here, really the key one is process automation. I don't know how many of you have seen or used HEEDS, but it really is very simple to create a workflow process. It's almost like dragging and dropping a flowchart onto a PowerPoint, almost like you see here. The actual HEEDS interface is very simple to use. You know, the process automation is the key piece. Distributed execution is also, you know, part of that, and that's really kind of where we're looking today to show you a process. But then efficient search and the insight. Efficient search is the Sherpa algorithm in HEEDS, if you're familiar with that. And then the insight and discovery is really just looking at the results. And you can see here, you know, this is multiple times around a design loop, and at the graph at the bottom in the middle, every one of those points, in this case, is an FEA simulation. And so HEEDS will basically plot, you know, the good and the bad results and give you this tide mark of, is it a good or a bad design? And so you can imagine this is a very automated process, and FEA is one way to do it. But then CFD is kind of the next level of that. And so when we look at CFD, then STAR-CCM Plus really is an enabling tool in this case, because it does allow you to do completely automated workflows, which is not true of all CFD tools, as we were familiar. So if we look at a case like this, which is an electronics cooling example, imagine we want to run an automated process on this, and we want to be able to move these inlets, we want to be able to move the fan, and we want to be able to adjust the geometry of the pins. Those all can be parametric variables. HEEDS can manipulate those and then automatically run the next STAR-CCM Plus model, and away it goes. And so basically, this is STAR-CCM Plus enables the HEEDS process really nicely. And if I run this, you'll be able to see what I mean, that each one of these is a single, fairly complex CFD simulation of heat transfer and modeling, but with different parameters for the geometry. And in this case, HEEDS is driving this totally, and that is controlling all of those parameters I've just described with the goal of maximizing the heat removal efficiency. And you can see that the meshing and everything else that needs to go into this is pretty complex, but STAR-CCM Plus handles that in an automated workflow. So the two tools together really complement each other well. HEEDS is great for process automation and exploration, and STAR-CCM Plus is perfect to enable that workflow. And so in this case, we see the high tide mark. I'm not going to play it all again, but when you look at the final result, you can see that the inlet vents have moved around to be more in the center, the exit fan has moved over to the left, and the geometry of the pins has changed. And so the cooling's improved, and that the mass of the heat sinks is also much reduced, obviously saving costs in material. And if weight was an issue, then that would be an improvement too. So this is a fairly simple STAR-CCM Plus model. Even though the geometry is complex, it's pretty simple physics. But then if you look at an example like this, which is a water pump to really just drive better designs, then it's kind of the same process, but basically applied in a different way, using CF Turbo as a geometry creation tool. Again, HEEDS can drive that, it can drive the geometry. And in this loop, we look at different water pump designs to really come up with something more efficient than the baseline case. And you can see again, this high water mark is improving it as it goes. But again, each one of these points, these dots here, is a full CFD simulation of this water pump. So as you can imagine, the compute resource going into this is considerable. And where do you find that resource is often the challenge. So let's look at another example, and this is really the last one I give before I pass it over to Eric. But basically, this is a marine example of a ship design, and it's part of a marine and HEEDS training class that we do. And what's nice about this is you can easily see this animation, all the variables that can be changed in this case. So you can see, I'm not going to read them through, but you can visualize exactly the variables that can be changed to look at the design of this. And really the goal is to fulfill the task at hand, to have enough deck space and enough volume to do what the ship needs to do, but also to minimize the resistance of the ship in flow, thereby saving money. And so this again is an animation of the same flow. And again, you can see HEEDS is driving the loop of workflow, and each one of these points is actually multiple simulations. But in the first case, it's a geometry creation of the hull. Secondly, it does calculation of the weight of the body based on that geometry. Then it does a hydrostatic calculation to basically get trim in the water. And then it does a STAR-CCM Plus model of the resistance. So this just highlights the idea that you don't just have to have one tool in this loop, it can be multiple tools. And really, that's another thing about HEEDS. It's so good at connecting multiple tools together. So this could also be, if you wanted to have an FEA model in this loop to look at strength of a component maybe after a CFD model, then you could do that too. So, but this particular case, you can imagine that the mesh and the STAR-CCM Plus model is particularly for the resistance calculation can be quite big. And so how do you figure out this workflow from when you're looking at the computers and the workflow that you need? And so here's the flow chart of that arrangement. And so HEEDS doesn't really need a huge computer to actually be able to run the scheduling and the parameterization of the model. And so HEEDS is controlling everything. It's the kind of orchestrator, if you want to call it that. It's controlling an XCAD model using the parameters I showed you in that previous geometry. Then automatically HEEDS is getting the NXCAD model to update the hydrostatics model in STAR, runs that. HEEDS again passes that result to the resistance calculation in STAR, and around it goes again. And so, but you can see that the compute resource here, for HEEDS is minimal. For the CAD, it's not too much either. It gets a little higher for the hydrostatics, but it's this resistance calculation that each job needs 24 cores, and HEEDS can run 8 concurrent jobs as part of this efficiency to do things faster. So 500 designs were run in 4 days, and really came up with a much better design, much better than you could get if you were trying to run it manually. But obviously not everyone has access to this kind of compute power. 196 cores, it's not a huge machine by today's standards, but it's also not the kind of machine that a small company or even an individual consultant might have access to. And so really the goal of today is to say, look, this is a fairly sophisticated optimization in this case. And then how can someone without access to big compute resource internally tackle this? And really the answer is to say, look, let's not have our own in-house computing. Let's use Rescale, and really that can be any cloud resource, but Rescale are friends of ours and really do well with linking to HEEDS as well. And so in this case, HEEDS can drive this process in exactly the same way, and actually control submitting jobs to Rescale. And that's really the value of today. So if you're a small to medium business or an individual consultant who wants to run really big projects, then you can do that. You can now do that using Rescale or a cloud-based provider. And now I put this slide in here. It's going to steal a bit of Eric's thunder, and he's going to be mad at me later. But this is basically what Rescale is, and it's a platform that connects basically general public clouds to just pretty much every engineering software tool you can imagine pre-installed. And so it's just very simple to run and very straightforward. And Eric's going to dive into that now, and then Chris is going to show us an actual example of us doing that after Eric's finished. So with that, I thank you, and I am going to pass the ball to Eric for him to show us a little bit more about Rescale.
Thanks a lot, Adam. I appreciate it. Hey everyone, it's Eric Timmer with Rescale. I am going to go ahead and share my screen, and I'm just going to show a couple different slides, and then I want to jump into the Rescale platform, or the Rescale interface, I guess, if you may. So everyone can see my screen. Jonathan, we're good?
Yep, looks good.
Perfect. All right, so just a quick overview on Rescale. So what we are is an enterprise simulation and HPC platform. So you might be thinking, well, we're not an enterprise. Like Adam just touched on, what we do is we really level the playing field, and allow those small and medium businesses to have the compute resources that an enterprise would have without having to invest in that large capital expenditure, right? So if you want to run on 1,000 cores, if you really need to speed up your jobs, you come over to Rescale and you choose that you want to run on 1,000 cores, and then you're only paying as that simulation is running. So we were founded in 2011, headquartered in San Francisco, a couple other locations throughout the world. A couple of our investors, Jeff Bezos, Richard Branson, Peter Thiel, just to name a few. And then you can see, the different industries that we work with. Really comes down to if you do simulation or if you do AI, machine learning, if you need additional compute resources, Rescale can help you. So, all of this stuff, let's say that you think about bringing in your own cluster or your own, data center. There's so many different things that go into it. Even if you wanted to go to AWS directly or maybe Microsoft Azure, there is a lot that you need to set up. You know, I talk to people on a weekly basis where, you know, they say, hey, I'm coming over to Rescale. I'm talking to you guys because I tried to do this on AWS. You know, essentially what you're trying to do is create Rescale on top of AWS. And they just throw their hands in the air and give up, you know, after two or 3 months of development time trying to do that. So we really allow engineers to just do their jobs. You know, you come over, you can be up and running that same day and have access to those compute resources that you're looking for. I kind of liken it to this. I really like this image, you know. So we've all been there where you're waiting in an airport line. You know, you're starting to worry, oh, geez, look at this line. You know, am I going to make my flight? You can see these people don't look too happy. You know, what Rescale does, and you engineers have all been there, you know, where you're queued, where you're sitting in a queue and just waiting for your job to be submitted. You know, what Rescale does is essentially, you know, we are kiosks. There are unlimited resources so that, you know, queuing doesn't exist with Rescale, which in turn makes engineers much happier and makes, you know, engineering managers much happier as well, because their employees are happy and you're getting results that much quicker. So we do have access to over 100 data centers. I think it's somewhere around 120 right now. We do have very strict security standards that we abide by. We even have a separate ITAR platform here in the USA, which runs on top of Amazon GovCloud. So we even do have, you know, weapons manufacturers that are running on Rescale right now. If we weren't, you know, if we didn't make security our #1 priority, we wouldn't be in business. So happy to go more in depth on that after this webinar, but just know that Rescale is very secure. So let me minimize this, and I'm just going to jump into what we call the Rescale platform. So what you're looking at right here is the Rescale interface. It's pretty straightforward. You know, really all that you need are 3 steps before you're solving your job, right? So when you're doing STAR-CCM, what you need is your .sim file. So I have already uploaded this. Most likely what you're going to do is just upload that sim file from your computer, and that's all that you need to do. You can move on to the next step, which is choosing the software. So we're going through a STAR-CCM example. You can see that not only do we have the latest version, but if you haven't, you know, if you need to go back a version, then you can just go ahead and do that. And then some people that aren't familiar with running in batch or haven't run in batch before might say, yeah, I don't know how to do it. I don't know how to run a command. There's nothing that you need to do. You know, it's already auto-filled the command line. So it's telling me that I can go on to the next step. Additionally, we do have other tools besides STAR-CCM. So you can see the whole, you know, gamut of Siemens products right here. And then the last step that you would need to do before you're submitting this job and the job is solving is choose the hardware. So this is really our bread and butter. As I mentioned, you know, the big differentiator between us and some of our competitors is that we don't actually own any of our own hardware. We are built on top of our cloud partners. So that is the AWS, Azure, Google, IBM. We partner with all of them. So for example, you see these are different hardware configurations, or core types as we call them, just different hardware options. You know, so like Onyx and Emerald right here are built on top of AWS. I scroll down and I see Magnesium and Mercury. You know, these are Microsoft Azure core types. So if, you know, some people will just say, no, I just care about cost and performance, getting my answers at a you know, reasonable amount. But if you do have things like a Microsoft agreement, you know, a lot of people have Microsoft enterprise agreements, then we can tie into that. And what we would do is limit you to, you know, Microsoft Compute so that you run against that. And so what you see right here are the specs on the machine. This is showing 8 GB of RAM per core. You see the interconnect right here, and then this is the storage per core. And then I have my price right here, 9 cents per core per hour. So I scroll down right here, and this is where I set the number of cores that I want to run on. You know, so whether it is, you know, 7 cores or 700, the beauty of Rescale is that that job is going to be solving within about 3 to 5 minutes. You know, no matter what number of cores. And really the nice thing about STAR-CCM is that the licensing for it is unlimited cores, and it does scale really well. So we do have people that on a daily basis are running 2,000 core jobs. Now, most people don't need that, but let's say that, you say, hey, I want to run on 154 cores. I have my hardware summary right here. I'm getting 1.2 terabytes of RAM, which is probably more than enough. And then I can see my hourly price summary. 154 cores is $13, under $14 an hour. So in my opinion, not too bad. And then of course, once you submit this job, if all you care about are the results, then I could hit this submit button and then shut down my computer. And then I'll get an email when the job starts. If I do want to do some job monitoring or some live tailing, this is a job that I kicked off right before the webinar started, I'm able to do so. So I do have the job monitoring capabilities even in batch right here. So I can see this update in real time. I could follow the output log. Good thing about STAR is that you can plot residuals, right? So all of this will update in real time. And then we get to the results page. So when it's done, looks like this. I can view any of the results that I want in browser, but most likely what you're gonna wanna do is just download the entire job, which is gonna zip up all the files and download those results back to your machine. One other thing that we have is a great administrative function, I guess, where you can do things like add team members. You could set up groups and projects. For engineering services companies, this projects is very, very attractive to them. So that you can say, all right, I want to create a project for customer A, another one for customer B, and then before you go to submit a job, you can attach that job to a certain project, so that the billing that you're doing for your customers, after the jobs are completed is very easy. I can see everything's very upfront. I have my billing summaries. It's pretty straightforward. Don't pay attention to this number. We do a lot of testing at Rescale, so this is actually our account. But if I really wanted to get granular, I could just download a CSV and see every single job that was ran, by every team member. Additionally, if you did want to do everything out of just on Rescale, maybe you don't have the hardware on site, even a laptop to do the pre and post processing. We do have remote desktops. So I'm right here in browser. I have STAR-CCM, where I could do everything from start to finish, pre, post, solve everything within our remote desktops. But my recommendation to keep costs down and really for the best user experience would be do the pre-processing, get the model set up, bring it over to Rescale to do the solving for you, and then download the results like I just showed a minute ago once the job is done running. So, Adam, I appreciate you letting us have time. I will stay on, and I guess, if there are any questions, either post them in the chat or write them down, and we can get to those once we're done.
Excellent. Thank you, Eric. We appreciate it.
Hey, thank you.
If you could stop the share, and then Chris, if you could pick it up, that would be great. Excellent.
All right. All right. Can everybody see my screen? It should be the title slide.
Yep.
All right. Great. Great. All right. As Adam mentioned, my name is Chris Ostoich. I'm an engineer with ATA Engineering. I have to start off by apologizing. I've got a particularly loud air conditioning vent in my office, so if that's coming through the line, I'm sorry about that. So the motivation for today's demonstration is a problem that was encountered in the mid-1900s as supersonic flight technologies were being explored. As aircraft were approaching the speed of sound, there was a large drag increase, which made it very difficult to accelerate past Mach 1. Breakthrough experiments showed SLIRN images, which showed standing shocks on wings, which created this drag increase in the form of wave drag. One significant breakthrough based on these experimental observations was the Whitcomb area rule, which basically stated that the cross-sectional area variation along the axis of the aircraft should have a smooth, should vary smoothly. And this resulted in fuselages that narrowed in the vicinity of wings, causing this Coke bottle shape. So this area rule was a product of decades of studying due to difficulties with experimentation and understanding in the transonic regime. The particular example that I'll talk about today is the development of the Convair F-102A aircraft. So in 1951, Convair began development on the YF-102, and although it was powered by the US's most powerful engine at the time, it couldn't push past the sound barrier. So after they did a redesign using area ruling, and make it all the way to Mach 1.24, resulting in the production version, the F-102A. So the question we want to answer today is, if they had the compute power and software in the 1950s that we do now, could HEEDS and STAR-CCM arrive at this result within a few days rather than years of hard work? So here I show the CAD model that I've developed in STAR-CCM's native CAD tool, and this is to represent, it's kind of a simplification of the YF-102 aircraft that was developed in 1951. I've parameterized the fuselage with 5 equally spaced mid-body radii, as shown, R1 through R5, and then the delta wing is just lofted between 2 symmetric airfoils. So I define those 5 radii as externally exposed parameters, and this makes them easy to change outside of the STAR-CCM CAD tool to easily create geometry changes, after which STAR-CCM can remesh, and as I show in the bottom here, I've changed 2 radii pretty substantially, and STAR-CCM has no problem remeshing. I just add here that I am using STAR's native CAD package, but if you wanted to use an external CAD package, that would also work. The next step in the process is setting up the model. STAR-CCM guides the user through simulation setup, and it's made easy through context-sensitive menus. Also, nice images can be generated using STAR-CCM's powerful and intuitive post-processing capabilities, and you can easily create reports to interrogate the solution for important engineering quantities. In this case, I've created a drag coefficient report, which I'll be using as a response variable in HEEDS. So here's an overview of my STAR-CCM computational model. It's 3-dimensional steady simulation. I'm using the ideal gas law and solving it with the coupled implicit solver, and I'm solving the RANS equations using the Mentor SST closure model. On the vehicle surface, I've got no-slip boundary conditions, and I'm taking advantage of quarter symmetry here, where the symmetry planes intersect along the vehicle axis. The free stream is Mach 9 at standard temperature and pressure, and the mesh is just under 409,000 polyhedral and prism cells. I'm running at a CFL of 20 and using advanced grid initialization, expert driver, and convergence acceleration. And I set the stropping criteria at 1,000 iterations, which on 8 cores on Rescale took an average of 30 minutes. So this note at the bottom, I'm just pointing out that this is a modest size model, and it was developed for this demonstration case, but the approach presented here can be scaled up to realistic problems. So now that the model's been generated, we move over to HEEDS. So the HEEDS Sherpa algorithm is a design space exploration algorithm which intelligently searches design space, in this case the 5 radii ranges, to determine, some sort of optimum. In this case, we want to minimize the drag coefficient. So in the table here, I've got my 5 parameters, and I'm allowing them to vary between 0.5 meters and 2 meters with a resolution of 101 along each direction. As I said, the response variable is the drag coefficient, and we want to minimize that. So an exhaustive search of this design space with this resolution would be around 10.5 billion simulations, which is ridiculous. But we've given Sherpa just 150 evaluations to find an improved design. So setup in HEEDS is made easy with analysis portals. The first step is to specify the process. The process can be made up of a bunch of analyses. In this case, since STAR-CCM is so powerful and has a native CAD package, a native mesher, the solver, of course, and then powerful post-processing tools, we only need the STAR-CCM analysis portal. However, more analyses can be added to the process. For example, CAD or a meshing package can be added upstream of the flow solver, and maybe an finite element analysis can be added downstream. After creating the analysis or specifying the analysis portal, input and output files need to be specified. In STAR-CCM's case, the input file is the output file. The model and results are contained just in one single file, so we just point to those for both the input and output file. One thing that's very nice is as soon as we point to that input file, HEEDS automatically detects those outwardly facing geometry parameters and suggests those as the variables that we play with in our design space. And then here on the right, I've just selected the drag coefficient report to use for the response variable, which we want to drive to a minimum. On the upper right, within HEEDS, we instruct STAR to use 8 cores, and on each STAR analysis, we tell it we want you to clear the solution, initialize it, and remesh it, then run. So HEEDS provides a Python-based API with which it can create a seamless interface to the Rescale cloud-based HPC resources. So you can see here on the window that we just select all of our Rescale options from within HEEDS, and our STAR-CCM runs are just performed on the Rescale cluster. In this particular case, we've defined an environment variable which points to our company's local license server where we already have STAR-CCM power licenses. However, if your company or if you don't have access to a STAR-CCM license, power on demand hours can be used in lieu of a traditional STAR-CCM license. So the setup steps on Rescale that Eric was going through, those are completely bypassed by this Python-based API. So as you run simulations on Rescale, you're burning through those hours that you're paying for. So this is the workflow that we followed and we recommend to reduce the risk of wasting your cloud computing allocation. I first developed a coarse, low-fidelity model that ran quickly on my machine, and it allowed me to run through a few HEEDS evaluations locally to find any bugs and troubleshoot. So my current example, I just generated an envisted simulation with a coarse mesh. After that all checked out, I then refined the model. I turned on viscosity, employed turbulence, and resolved the boundary layers. And then I plugged that high fidelity model into my already proven HEEDS project. Then I just used cloud computing resource and the horsepower that it provides to optimize the high fidelity model. As Eric showed, you can log on to the Rescale platform and monitor the process of each one of these analyses within the HEEDS optimization. Here I just show a screenshot, the same as what Eric showed, tailing the simulation output. All right, so during this design space exploration, HEEDS updates the progress in real time. So you can see the objective history here. It shows a dot for each STAR-CCM analysis, and as it navigates the design space. We started with evaluation 0, which is the baseline case, and in this particular case, we found that evaluation 32 had the lowest drag coefficient and improved the fuselage to result in a 38% reduction in drag. However, one issue is that I am still part of the process and I'm human and make mistakes. So I set the stopping criteria to be at 1,000. You can see here on this monitor plot of the drag coefficient that this evaluation hadn't really converged yet, and the drag coefficient was oscillating, and at 1,000 the oscillation happened to hit a low point, indicating that the CD was actually lower than may have been the case for this design. HEEDS provides powerful post-processing tools to help me make up for my mistakes. I was able to filter out the top performers and determine the solution that was actually right. And this, isn't just for the case where you make maybe an input mistake. If you have a number of top performers and some may be easier to manufacture than others, then you can very quickly filter out the top performers and scan through the ones, scan through them to determine which one works for you. So very quickly I was able to find the 1% top performers and found that there were 27 designs in that range. And so I found that evaluation 79 had converged and resulted in a 35% reduction in the drag coefficient from the baseline design. So that's a win. So now just a note on scalability. This small demonstration case took 799 CPU hours to improve the design 35%. And this was done over 150 evaluations, which took 4 days with minimal analyst setup. Using the resource Onyx, we paid 12 cents per CPU hour. So the hardware cost to improve this design was $95.83. This isn't including the cost of STAR-CCM plus licensing. So assuming perfect scaling, a similar 20 million cell study would cost $4,700 on 400 cores. And this is really highlights the benefit of this approach to a small and medium-sized business. If you wanted to do this on an in-house cluster, that 400 core cluster would cost around $200,000. And this is assuming that you had a room set up with sufficient cooling and clean and reliable power. There was an existing network with safe, reliable, and fast storage. The racks existed to hold the HPC hardware, and a dedicated staff member with a full-time employee salary would be needed to maintain the system and infrastructure. So in summary, we want to design an aircraft fuselage with a lower drag coefficient in transonic flight. We use HEEDS design space exploration software with STAR-CCM plus Flow Solver, utilizing Rescale cloud-based HPC resources to find a better design. This virtually hands-off method produced a design with a 35% reduction in drag coefficient, and he's produced an improved aircraft design based on high-fidelity STAR-CCM predictions with minimal analyst effort, utilizing affordable Rescale cloud-based HPC resources. So that's the end of that demonstration. I'll pass it back over to Adam and take any questions.
Excellent. Thank you, Chris. That was great. Jonathan, can you unmute the microphones online?
Yes, yeah. So if you have a question, you can certainly enter that through the chat, and we can address those with the chat. You can also unmute yourself as well. So you can either click the button by your name to unmute yourself, or down in the bottom left, there's also a mute or unmute button. So if you have any questions, you can also now unmute yourself to ask those as well.
Anyone in the audience have questions? I wanted to mention something about STAR-CCM Plus licensing. Power on demand is the easiest way to use STAR-CCM Plus on any cloud on Rescale, because it really doesn't need a FlexLM license server set up. It can just ping the Siemens POD server. So that's the easiest way to go. But we actually used it to connect to our own ATA's license server, so that we could use our own in-house licenses. And really, so any client who's already got STAR could potentially do this as well without really incurring any more cost, specifically by connecting to their own licenses. And so there's lots of ways to go in terms of unlocking the STAR-CCM Plus licensing piece.
Yeah, and this is Eric again. To add on to that, Adam, I'm not even exaggerating when I say if someone called me and said, we have STAR Power on Demand licenses, that we could have them up and running within 5 minutes, being tied into that CD.ATCO portal. So I really can't stress how easy it is if you already have the STAR licenses.
So with that, thank you all for attending. We'll also be posting a recording of this to our website in the next couple days. So if you're interested in reviewing part of it yourself, or you want to share it with a colleague or anything, certainly keep an eye out for that as well. Thanks, everyone.